Hi everyone, good day. My name is again Edmian 3Bagain from BSED Math 3B, and allow me to present to you my geometric model in partial fulfillment of the subject M115 or abstract algebra. So again, the title of my model is crystal symmetry. It is based on the snowflakes because again one day I want to be able to experience the real snow. Okay, so we have here the elements. For front we have ILYSOMED, and for back we have 1436257 8. And if we rotate that, or the back after rotating would be 1875264, or like this 1436257 8. Okay, so now we will be looking at the symmetry of my crystal symmetry model. We have for front and we have the back. I is symmetric to 1, L is symmetric to 4, Y is symmetric to 3, S symmetric to 6, O is symmetric to 2, M is symmetric to 5, E is symmetric to 7, and D is symmetric to 8. And now let's enter this one. So after After knowing and identifying what subgroups are cyclic and not, let us now relate the order of groups and the order of subgroups, which is the project number 4. So this one would be the next one. So the order of a group H is the number of elements in the group donated or denoted as this. So it is denoted like this one. H, or it looks like two lines and the H is inside it, and that would be it. So this one, it talks about the order of the group H. Okay, so the order of the group H as provided in this project, as we can see, is the number of elements in the group. Okay, so how many is this? So we have here H is equal to 16. Okay, and those H, or the group H, is has the elements ILYSOMED 1462578. Okay, so this one. And according to Lagrange theorem, for every subgroup of G of a finite group H, the order G divides the order of H. Thus, the possible order of groups G of H are the divisors of 16. Okay, so now we will be talking about what are those divisors. We have these divisors are starting with 1, next 2, next is 4, next is 8, and next is 16. So all of these are the subgroups or the possible orders of subgroups of G. So have all of this number of subgroups of order. Okay, now let's verify the orders of the subgroups identified in the project. We have the improper subgroup of H, which is the H is equal to 16. What would that be? We have the next one. We have the H sub 1, which is equal to ILYSOMED. And how many elements would that be? 8. Okay, so now we know that we have the 16 and the 8. And next we have the 4, which is the H sub 2. H sub 2. This one, the H sub 2. Let's check. We have the 4 elements as well. Okay, so next, H sub 3. It also has the 4 elements. Okay, So for the next one, we will be talking about the order of 2. Okay, so each has order of 2, which is also a divisor of 16. So we have the 8 sub 4, 8 sub 5, 8 sub 6, 8 sub 7, 8 sub 8, which is I and 5, 8 sub 9, which is I and 7, and then 8 sub 10, which is I and 2, and then 8 sub 11, which is I and O, 8 sub 12, which is I and 8, and then lastly, as we can see, from H sub 4 to H sub 12, we have the order of 2 of a subgroup. Okay, each has order of 2, which is a divisor of 16. And lastly, we have the trivial subgroup, which is the H sub 13 is equal to I. And I, how many elements would that be? Only 1. That is why the order of H sub 13 is equal to 1, which is also a divisor of 16. So, as we can see, therefore, we can conclude that the order of the group, which is 16, is related in the order of its subgroups in such a way that the order of the subgroup is the same as the divisors or factors of the order of the group. Okay, so that is the conclusion. We know that when we are talking about the orders of the subgroup, or when we are relating the order of subgroups to the order of the group, it is just that it is the divisor of the main or the order of the group, which is the 16. That's why we have the 1, 2, 4, 8, and then 16. So thank you so much for listening. Again, my name is Edmay and 3Bagain, and have a great day.